time to look at some of the theoretical aspects of the Coulomb's Law Lab and how we're going to be able to do some calculations in order to show this relationship between two charged objects and the strength of that force versus the distance between them. So we have this experiment where we're bringing this ball on a stick closer to another ball that is hanging. Both of them have the same type of charge on them, and we're going to get this repulsion. And the one ball is swinging up and away. So that's going to complicate the mathematics a little bit, but it's not beyond what we've already looked at for this class and the previous semester. So we start in our initial case. We have the ball on the stick is pretty far away. Far enough away that there is no electric interaction between these two objects. So we'll say at this point, any forces are too small to really be felt. We can say that this initial hanging location is maybe some x0. In general, we're going to define where this ball is as x1 and where this first ball is as x2, this first ball is x1. So x1 here is that location. We'll say this is x2. But at this point, it happens to be equal to some x0, some initial hanging location. There's going to be an important reason to consider that some x0. And the distance between the two balls is r. So this is the r that we refer to in Coulomb's law. So some distance r. So that tells us that r is equal to x2 minus x1. Now, if we take this ball and we bring it closer, the hanging ball is going to feel that and is going to begin to repel and swing outward. So this is where we want to look at that aspect of it. So we slide this other ball forward. And let's say that initial x2 was right here. But now the second ball swings outward, so it gets pushed out to here instead. And now it's hanging at some particular angle. It's not a very realistic picture. If x0 was originally here, then that means it was straight above. That's a bit more realistic. So again, we're going to have some position x1. This is now going to be our position x2. The separation between x1 and x2, still r, we referred to it before. But now we're going to look at how far this ball has moved from its original position. So that's going to be our position x. So we might draw that here. Say this is some distance x, where x is now x2 minus that initial x0. So those are the two distances we're going to need. How far has this ball moved, and what is the separation between these two balls? We need to consider a free body diagram for this hanging sphere as it's pushed aside a little bit. That is where all the physics is that we're going to be able to pull out of this situation. So let's say we're initially hanging like this. Then when it gets deflected, it's hanging over here. And it's up a little bit higher than it might have been at this bottom location. Force-wise, though, we're looking at three forces. We have Fg, force due to gravity. We have a repulsion, so F sub E, the electrostatic force. And we're also going to have a tension force F sub T, that is up and to the left in this case. And we know that there is a balance here. This ball is not accelerating. Therefore, the forces are balanced in both the x direction and in the y direction. So we know we have to resolve Ft into an x component and a y component. So doing that over here, you can say Fg is down, F sub E to the right. We don't know these two are equal. I happen to show them as equal looking lengths, but they're going to have very different values. So if the tension here is some Ft, then we know there's an x component, Ftx, where ideally these two are the same length. maybe I make this a little bit shorter to make sure that looks about the same length. And then FTY is some component upward. Now, if we want to determine sines and cosines for FTY and FTX, we have to see, well, what is the angle that we're measuring? And typically in this experiment, we would look at, well, this angle here that we swing from 0 degrees when it's hanging perpendicular, or when it's hanging, straight up and down, we would often refer to this angle that it swings outward. So in that case, in this triangle here, we can see this is our angle theta. So when we look at this triangle, we could say that this y component over the hypotenuse, FTY over FT, is equal to the cosine of the angle. So that shows us that FTY is then going to be FT times the cosine of the angle. Whereas FTX, that's going to be the sine component. So I'll put that over here, FT times the sine of the angle. Now, often in physics, we try to work with it such that the x-axis, the angle is elevating from the x-axis, in which case usually cosine is what represents the x direction. But in this case, since we have this upper angle, it turns out that sine is going to be representing the x direction. Okay, from here, now we can start writing the balance of these forces. So we see that FTX must balance FE, and FTY must balance FG. Okay, some of the forces in the y direction must be equal to 0. There's 1 up minus 1 down equals 0. That means those two forces are equal. So on the y direction, we have FTY is equal to FG. We know FTY is FT times the cosine of the angle. And FG is just m times g. In the x direction, some of the forces in the x direction also is equal to 0. One force to the right minus another force to the left equals 0, so that means these forces are equal to each other. FTX is equal to the electric force, which is the force that we are interested in finding out about. FTX is FT times the sine of the angle equals FE, which is unknown at this point. So we want to solve for FE and find out what that looks like mathematically. So there's an unknown FT in both of these. So what I can do is I can take this equation, solve it for FT, solve it for the tension, and plug that in over here. So dividing by cosine theta, bringing this over, I have mg over cosine theta. And now I can take this term, and I'll put it in right there. So we have, this FT is written as mg over the cosine of the angle times the sine of the angle equals the electric force. And now there's going to be a really nice simplification. That sine theta over cosine theta is just the definition of tangent. So we can write this as the electric force is equal to m times g times the tangent of theta. I'm a little afraid this might be slightly out of the camera shot, but I'll try it anyway. So Fe is equal to mg tangent theta. Okay, summarizing where we are, Fe is equal to mg times the tangent of the angle. That angle is tough to get at. I mean, we can do it, we can measure this distance, measure that distance, we can find the angle, but there is a nice simplification that we can do here. By knowing that the angle that this ball on the string swings up is a pretty small angle. So if it starts by hanging straight down, and then it gets deflected over here, we know this angle is theta. This length of string is L, so we know when it swings upward, this length here is definitely the length of the string L. We're saying that this distance that this ball, let's go here, this distance that this ball goes over, that's the distance x. So technically, our triangle goes from, so we have a right angle here, and this x is a little bit above the center of this ball. So it's not perfect. This length along here is not actually L, but it's pretty close to L. This is approximately L, this length here. Because you'll see, even when it swings up just a little bit, it's only a little bit higher, so this is a very short distance that is lifted up. So this length, starting from here, is pretty much L. So then we can, using this triangle, we can figure out, well, what's the tangent? Tangent is opposite over adjacent. So x divided by this term that's basically L is the tangent of the angle. It's approximately x over L. And now we can put that up here, and that lets us say that the electric force is equal to mg times x over L. Or, basically, it's some constant times x, which is the assumption that we want to make in this lab, that we want to say that the electric force is proportional to the distance that that hanging ball moves over, because that's really easy to measure. All we need to do is measure the location of ball 1, location of ball 2, and, well, actually, no, not for x2. All we have to do is get the location of ball 2. x2 minus its original position gets us what that distance x is. So that distance x tells us what the electric force is. And then the distance between the two balls, x2 minus x1, that's the distance r. So now, when we make a graph of x versus r, that's effectively making a graph of the electric force versus the distance r.